materials that are stationary with the free electrons and the sea of electrons, where we have these charged particles that are free to move under the experience of electrostatic field. So metallic bonding, good electrical thermal property. Next in line, we have dielectrics. Those typically are going to involve the transfer of electrons. In the case here, sodium fluoride, sodium is going to donate an electron, fluorine is going to accept it. And those
Professor Alford,
yes.
we're still having a hard time hearing you. I don't know if there's like pods or anything else we could try for the audio.
I can take these off. I mean, the other ones, it's not working. We try this. Yeah, we've had really bad internet over here in the last couple of days.
I can actually hear you a lot better right now. Did you just change something?
I don't know which is which.
Whatever it is now is working.
Okay. All right. So with the case of dielectrics, we have ionic bonding. So in that particular case, all the electrons are involved in bonding. So there are no free electrons. So these types of materials, we would expect them not to have good electrical conductivity. What we would expect from them to be good electrical insulating materials. Okay, so we'll see that in our dielectric as well as in our insulators. Then we look at silicon. It has directional 3D covalent bonding. So that means it's going to be very, very strong, hard. And when we look at thermal properties, it's going to have a low coefficient of thermal expansion. Now, the opposite would be the case of the underfield, which is a polymer. If we recall from our discussions about polymers, we have linear covalent bonding along the backbone, and then van der Waals bonding between the backbones. Okay, so that is weak bonding. So it's going to have a low melting point, and it's going to be soft, okay, at room temperature. All right. So now, if we continue on, we have to think about it. We talked about how we went from lead frames and these dual pin packages all the way up to the 3D packages. Now, as the packages evolve, materials are going to have to evolve because we're going to change form factors, and that's going to lead to higher stress. We have to mitigate the stress as much as possible. And then we have to talk about use conditions. We look at that dual pin, probably wouldn't do well under the hood. But now we have to have packages such that they can serve in various environments, one of them being under the hood. So we have to be able to design packages and materials for such. And then when we get to assembly, there's going to be some issues about like the interposer. If we're going to use silicon as the interposer, it's going to take some effort to etch those through holes and then plate and fill them. Previously, we talked about power and thermal management. As we go to smaller and smaller footprints, form factors, the power density is going to increase because we're going to definitely increase the density of our transistors. And if you recall from the example we had, for just one clock cycle, and we only have 20% of the 1 billion transistors toggling, we would generate 600 watts. So that's a lot. And if we're doing that over and over again, we got to be able to get that power out. Okay, so it's going to require new materials that can be used as TIMs or the heat spreaders. Quality and reliability. Bottom line, people want their product. If they're going to pay money, they want their phone to last a long time. They want that TV to last a long time. They want that server to last a long time. So we got to build in quality and reliability and the utmost cost. So what does this mean? Regardless of the evolution, regardless of the product, we will always depend on materials for packaging. And we will also have to see the evolution of materials to keep up with the need to move from flip chip to 2.5D to 3D to 3D embedded. So again, materials have to drive the innovation. Now, we see that we have the schematic of a package. We go from the heat spreader. So bring it over here. We go from our heat spreader to our TIMs to the die, where the transistors will reside on the surface. Okay. Then we have our first level interconnect, which are the C4 solder balls. Then we have a printed circuit board, composite material of polymer, epoxy, and metal. We have our die side components, as well as our land side components. Now, all of these are different materials, whether we're looking at copper metal for our integrated heat spreader, graphite for our TIM, silicon for our die, silver, tin, silver, copper, solder balls, okay? So we have a variety of materials that we need for our package. And we need, they have to be there to help us meet this need for innovation. As I said, we're going from 2D to 2.5D to 3D heterogeneous integration to embedded heterogeneous integration. We got to be able to manufacture. Again, we have to have quality and reliability at every level. Okay? So that means we have to have proper material selection. Okay? And that means our portfolio will have to be diverse as such. That means we're going to use metals for interconnects, solders, heat sinks, TIMs, and fillers. So like in the case of, if I look here at this underfill, I got the underfill, which is a polymer. I can actually add some metal powder to help improve its thermal conductivity. Okay. We're going to have ceramics in if we have a ceramic substrate, or we would definitely have ceramics as dielectric materials in our capacitors. Polymers will be utilized for substrate. Like here's a printed circuit board. We have our TIMs, encapsulant. We'll see those later on, as well as adhesives. Okay. Now, in each case, the reason we select these things, because we are interested in performance in a variety of things. With the two most important ones, looking at electrical performance, in the case of dielectrics, metals, ceramics, whether we're making inductors, die-side capacitors, land-side capacitors, they're needed for the voltage regulators. Think about thermal performance. As we said, we could generate 600 watts. And then moving by 2030, the year 2030, we will be producing 400 watts per millimeter square. That's an enormous amount of heat for 1 millimeter square of silicon. Yeah. Now, then we will have to be concerned with our thermal performance. And in that case, we're talking about heat sinks. We need things that can move a lot of heat very quickly. And we see here, if I look at my copper integrated heat spreader, in this particular case, copper, great electrical conductor and great thermal conductor. Here, I want a large surface area so I can get a lot of convection, heat transfer, and then I want good intimate contact with the tin and the silicon such that I get good conduction thermal transfer. So we could also have some of our TIMs, we will use polymers, especially if we're in a situation where we're going to see some very high, I should say, very large differences in coefficient of thermal expansion. So in that particular case, we'll utilize some polymers. And thermomechanical and environmental protection. That lid on top of the package has a function. It's there to protect it from, when you drop it, or if, for God forbid, something falls on it inside of the package. And then thermomechanical protection. These things will see a lot of different temperature gradients, temperature cycling in such a manner that we will produce thermal stress, I should go the other way, thermal strain, which induces thermal stress. And those stresses can be greater than the yield stress, such that we can actually induce failure. And this failure could introduce itself by fracture, it breaks, or you just have plastic deformation where you just change the dimension. And that's not good because, as we said, we get this thermal stress, and we'll see in a few minutes that it can actually impact our performance as well as the lifetime and reliability. And in the process, we say that all materials must be processable, meaning if I go over here to the underflow, what I want it to do, when I already have my chip connected, I'm going to put some polymer here. And then when we go to cure, I want it to be able to flow under and fill in between the solder balls, as well as the edges. And then by doing so, it provides mechanical stability and a little bit of heat transfer. Now, with that being said, we say the material has to be processable. So let's look at this case of cure. Once I already have the solder balls down, I don't want to go to a very high temperature because they're metals, low melting point metals, so they will flow and lose mechanical stability. So I got to be able to find materials that I can process as at low a temperature as possible. Now, because if you came in and said, well, we're going to, try to flow, we're going to put some ceramic material and use it as the underfill, won't happen because you'd have to go to such incredibly high temperatures just to get it to flow under. So it won't work. Okay? So we have to know a lot about different types of materials so that we know when to use them based, again, for whatever performance we want: electrical, mechanical, thermal mechanical, as well as environmental protection. Now, here's an interesting question. We have to find solutions to our challenges, and we're going to have challenges regardless. Excuse me. Green manufacturing. When you try to open up a semiconductor plant, manufacturing facility, excuse me, first permit you have to do is get water. And you have to show that you're able to reuse your water over and over and over again, such that you're not always garnishing water from the community. So you got to be able to use your water over and over again. And you have to use processes that are clean, such that they don't produce a lot of hazardous waste. Okay? Then you really need sustainable processes. These are processes that we know they can go, they don't use anything that's limited. Okay, like silicon. Silicon comes from sand. Got plenty of sand. There's no shortage of sand. It's got to be the right type of sand. Okay. However, let's go to the other extreme. Get out your fancy cell phone. Okay. Well, that transparent conducting oxide, indium tin oxide, is transparent, but it's electrically conductive. That's what you need, such that you can press on your phone and make all these magical and mystical things happen. Well, unfortunately, Mother Nature is not making any more indium. We're pretty much, all the indium we got now there's only a little bit more out there, relatively speaking. So we're going to have to come up with new ways of having these transparent conducting oxides for our phones, touch screens. There's just not enough indium. So that's going to be a great challenge to actually find a replacement. And often we have to think about, they have to be ethically sourced material. Chrome, vanadium, they're typically coming from places that are dealing with war, unfortunately. So we have to think about, can we utilize materials that do not come from war and torn regions or places where it's just unethical by the means to get those materials. Then we have to repurpose our material or recycle, one or the other. And so let's take a moment for inquiry. Which is better for recycling, thermoplastic or thermoset? Or they're both equally possible, or neither? So let's take a poll and get your opinion. Brittany?
Yes, I'm working on it. One
Okay,
sec.
no problem.
There we go.
Okay, we have 20 more seconds. Ten seconds. Okay. So. Okay. All right, so most of you all said thermoplastic. Let's go back and see why. Well, a thermoplastic is like water. I can heat it up, cool it down, go from ice to water, ice to water, ice to water, ice to water. I can do that an infinite number of times. And that's what we have with thermoplastics. Okay. They can be heated up, molded, cooled into a shape. And if we want to recycle it or use it for something else, we can heat it up and reshape it. So thermoplastics are like water, ideal for recycling because you can heat them up over and over again. Thermosets, however, are like an egg. You heat it up one time. That's it. That's the form it's going to stay unless you keep heating it up till you burn it. So you can always think about thermoplastics are like the water. Heat them up, cool down, recyclable. Thermosets, heat up one time, you're done. Now, thermosets can be repurposed. Perfect example, automobile tires. They are heavily cross-linked polymers, so you can heat them up or vulcanized rubber. That's it. Only thing you can do is keep heating them up and burn them, but you can repurpose them by cutting them up and then pressing them together with some adhesive. Now you have a nice outdoor playground floor. Okay, it's nice, bouncy. You fall, you don't get hurt as badly. Okay, so that's moving forward. We got to really think about this recycling and repurposing. So we talk about which one is best for recycling. It's the thermoplastics. Okay. Now, see if we were actually listening last week. We have another moment for inquiry. Which feature is typically not a landside feature? Underfill, capacitor, first level metallization, all of these, none of these. We'll take our second poll. Here we got 10 seconds. Okay, so we have a variety of answers. And okay, first level metallization, okay, or first level interconnect is not land side. That's going to be die side of the plated circuit board. And if we have to go back and take a quick look, so we didn't do as well as we should have done on that one. Okay. All right. So let's go. All right. So in summary, our package will have a variety of materials. They will range from composites, which are utilizing two materials to obtain a desired a desired property. We'll have metals, metal lines, metal traces, solder balls, integrated heat spreaders. Again, taking advantage of metals in their metallic bonding. Ceramics, we can use those for dielectrics, and we will definitely use those for our ceramics, insulators. Polymers will have a variety of properties, a variety of usage, ranging from chems to encapsulants, printed circuit board. But I should say, regardless, as the package continues to evolve, as the customer use conditions evolves, technology evolves, materials have to evolve as well. All right, so I'll stop here. Any questions? Okay.
Professor,
Yes,
I have a question.
sure.
What are the future outcomes we are expecting from the green manufacturing?
What are outcomes?
Yeah, future outcomes we are expecting from the green manufacturing.
Well, from green manufacturing, what I to answer what am I expecting? I think I'm going to expect what they're going to have to do. Going to have to come up with ways to utilize less water. Okay, water for you got to remember, water is a very valuable thing, and and I should say, be able to reuse water, water management. That's going to be first and foremost. And then try to come up with processes or manufacturing processes that do not produce a lot of waste. So we got to be able to do things like additive manufacturing, where we add to it. and we add to the product, as opposed to subtractive. Because if we have to add, then subtract, what do I do with this content that I've subtracted? Can I recycle it? Can I repurpose it? Okay. But if it's just going to be waste, that's not good. And then we got to come up with ways where we utilize better materials of, it would, for the heat spreader, it would be perfect if we could actually utilize diamond. Best bulk heat transfer material known. But trying to get natural diamond and then try to cut and polish it for a package, really difficult. But can we make it? Well, we can do plasma enhanced chemical vapor deposition. And in as much, yes, we can do it, but that usually involves some really nasty gases. And then when it's time to clean after that deposition, you have, unfortunately, you have some hydrocarbons, you have some graphitic-like carbon that could be on the surface. Now we have to clean that. One of the things we have to find out is how to come up with some very safe cleaning, because right now, to try to get that graphitic carbon off and some of those hydrocarbons, it takes some really nasty acids, some bad cleans that involve several nasty acids. So we wanted to get to a point where we hope that we can start utilizing processes that do not involve as many, acids, because one of those things, both of those nasty acids are carcinogenic. So unfortunately, they've been known to actually produce, to cause cancer in people. So that's another thing. We want to try to get away from utilizing any types of solvents or whatever that are carcinogenic. And then energy. Unfortunately, I would say for the last 50 years, semiconductor companies really didn't care about their energy use. They were like, whatever the electric bill is, we will pay. And communities allowed them to do so. But in recent years, communities are saying, hey, everybody's got to do their part in terms of managing
Thôi thôi ơi, không được
energy
gì.
Trời ơi. Yeah, please mute your mic. Thank you. So yeah, we got to recently said everybody has to be involved in energy management. So fabs or assembly facilities are going to have to try to be more energy efficient and utilize power or manage their power usage by time. If we could actually, I can say like on the front end, most fabs run 24/7. So it's not a lot we can do there other than try to come up with energy efficient tools, energy efficient processes. Even on the back end, in the packaging, we just have to try to come up with energy efficient tools, energy efficient processing, manufacturing. And as I said earlier, and then try to come up with materials that are not scarce. Because as I said, with the indium tin oxide, we got to come up with a better way to create it. But by coming up with this better way to address that materials issue, we still have to come up with a very green or clean process. Because we can't solve one problem by creating another problem. So I hope that answers your question.
Yes, I got it. Thank you.
Oh, you're welcome. Okay. Ooh. Okay. So can you see my screen?
Yes. You
Okay,
can see.
thank you. All right. So now we have another moment for inquiry. If I have a stiffener, it's going to be made of what? And what is the function of a stiffener? Okay, we got 15 more seconds. Oh, I've stopped the boat. Oops, I went too far. Okay. Now, why did I put this moment of inquiry at the beginning? For you all who will be developing curriculum, as I've said before, my classes are designed for online course delivery. And when we utilize the moment for inquiry, it's a way to gauge the level of comprehension by the audience. Now, one of the things you can do is to encourage your students to review the slides before the lecture, okay, before they start the lecture. And reason being, you may not have a textbook handy or you know, there may not be experts in this area. But what we want people to do is to review the lecture notes before they come to class. And one way is try to engage them in such a manner to encourage them to actually look at the lecture notes before class is to, at the beginning of the class, put up a moment of inquiry where you ask them a question that is going to be covered in the class. Okay. And in this case, typical stiffeners is going to be made out of steel with the aim to prevent warpage. Okay. And we'll see that. All right. So a lot of what is of interest to us is going to be thermomechanical performance. Okay. Thermomechanical properties are critical to the performance of the material of the package and its reliability. Thermomechanical properties. These are mechanical properties that are sensitive to temperature rise or temperature reduction. They're sensitive to loading at elevated temperatures. So When we talk about thermomechanical properties, they have to be mechanical properties that are sensitive to changes in temperature. Coefficient thermal expansion. And we'll see fatigue and creep as well. We looked at Young's modulus. That is the linear portion of the stress strain curve. Okay. And if you recall, it is related to the materials bonding and how that bonding reacts to mechanical loading. So in the linear portion of the stress strain curve, that slope is your Young's modulus. And so in the linear portion, Young's modulus. Now, another one is our glass transition temperature. Glass transition temperature for a solid is when we go from a glassy phase to a rubbery phase. Okay, so remember, if I take my tennis ball at room temperature, I can bounce it, bounce it, bounce it. But if I put it in liquid nitrogen and I cool it below its glass transition temperature, it turns into a glass. So when I try to bounce it at the low temperature, it shatters because it's a glass. Also, when we look at our glass, when we look at our glass transition curve, it's usually plotted temperature versus log of the modulus of elasticity, or normalized modulus of elasticity. And you see, when I go from the rubbery stage through the glass transition, my modulus goes up, my strength goes up. However, I lose ductility. So I cannot absorb energy. So that's why when I take the tennis ball, I dip in the liquid nitrogen liquid nitrogen, and I cool it below the glass transition temperature. It gets stronger. However, it's a glass and it gets brittle. Boom. So I try to bounce it, it shatters. Whereas if I'm in the just below the glass transition temperature, still sort of rubbery, but stiff, I will have the typical stress strain curve for a crystalline solid. I'll go through yield stress, then some elongation till finally I get a fracture. So I'll have at failure, I have a ductile fracture because I'll go through the linear portion, then I'm out here ductile, I'm undergoing plastic deformation until I have fracture. Okay. So now we have to really consider coefficient thermal expansion mismatch. So when we have adjacent materials intimately touching, okay, and we have changes in temperature. Okay, you remember we're talking about thermomechanical properties. These are properties that are sensitive to temperature changes. Okay. So here, if I have differences in coefficient thermal expansion, I can introduce compressive or tensile stress during testing, during service, during transportation, because do not forget, we live in Arizona, or we live, I guess the folks in Costa Rica, it's warm, unless you're up on San Jose, up on the mountains, and most other places going to be warm. So during just transportation and storage of packages, before they're put in service, before they're put in the laptop, they have to be able to handle just the ambient temperature changes, as well as deal with the temperature changes when they're in service. Now, from these thermomechanical stresses, you get stress-induced fatigue. That's failure due to cyclic loading. And take a coat hanger, bend it, bend it, bend it, bend it, bend it. Bend it. It gets a little tougher every time, but eventually it'll break. That's fatigue. Okay. Crack nucleation and crack propagation can be enhanced by stress. And we've already talked about warpage. That's what you don't want. But unfortunately, warpage will occur. That's why we will utilize stiffeners. And so with all this going on, we have to be able to manage material interactions. And how do you do that? First, you got to understand the material and understand its properties. So if we go over and start looking at different materials and we look at their coefficient of thermal expansion in units of parts per million per degree C, and then we look at our moduli of elasticity in gigapascals for a variety of materials. So let's start off with our good friend, silicon. Coefficient of thermal expansion is 2.7. You say, why is it going to be low? Well, what type of bonding do we have in silicon? We have 3D directional covalent bonding. Very, very strong. Okay. That's the same type of bonding that is in diamond. Same type of bonding in silicon carbide, boron nitride. Okay, so this directional 3D covalent bonding, very, very strong. So it's not going to be very as sensitive to heat temperature changes as, say, a metal. So let's go over here and look at the metal, copper, aluminum. Almost 10 times the coefficient, well, I should say 8 times that of silicon. So for the same amount of heat, they will expand 8 times as much, or will want to expand 8 times as much. I go over here and I look at this 1037 lead. So that means a 10 lead solder with 37% lead. Okay, so with this is all metal, but it's soft metals. So its coefficient of thermal expansion is going to be larger. We look at lead-free. This is 10 with almost 4% silver in it. Soft metal. Again, coefficient of thermal expansion is high. Now let's go back to a ceramic here. We have alumina. Okay, alumina has some coefficient, we'll have some covalent bonding in there. So it's going to be a little lower. Has a little bit of ionic. So the coefficient of thermal expansion is higher than silicon, but not as high as the metals. Now we can go to silica or silicon dioxide. Again, another, it has crystalline silicon, has 3D directional covalent bonding. And look at that coefficient of thermal expansion, 0.5. And then we got fire resistant 4, which is a substrate. It's a composite, typically most often a composite. So it's going to be in between die attach, soft polymer with metal filling. So it's really high. Some of our dielectrics, polymer dielectrics can be high again. But yeah, if this is a polymer attach, high. Polymer, high. We know our underfill is going to be a polymer, usually filled with some filler. So it's going to be high. Mold compound, high. Okay. So we can see we can have a variety of coefficient of thermal expansion throughout the various types of materials. Now let's go over here and look at the moduli of elasticity. Silicon, 107. Now remember, silicon is brittle, so that slope is in a linear regime. So we're not going to get any plastic deformation. So as you load that silicon, it's going to, when it's linear, it's just going to remain elastic till fracture. Whereas copper, I look at the modulus of elasticity, it's high. But now, but copper is soft. Now remember, this is just the slope in the elastic regime. Look at aluminum, 79. Look at the solder, tin lead solder, 54. But now I look at alumina, okay? Look at this modulus, 345 gigapascals. So that means that thing does not want to, very strong. Silicon, 120. But if I go back to polymer, 20. Die attach 4. So imagine if I have this die attach, and excuse me, and we'll come back to an instance where we're going to put the die attach in contact with either alumina or silicon. Dielectrics, these polymers. Here I can tell you all of these moduli are small, so that means they're polymers, okay? Or very, very soft metal. But here to get down in the 20s in single digits, definitely polymers. If you're in the mid 50s, very soft metal, okay? And then we increase in strength till we get to covalent bonding materials like silicon, alumina, and silicon. Okay. So now we got to look at what happens when we put these things in contact with one another. Okay. Well, here, now if I look at my TIM, that's my thermal interface material that couples two interfaces for the heat sink, okay? Thermal conductivity, that's the rate at which the heat is removed from the medium, okay? Then we want and make sure we get these units, watts per meter Kelvin, big K Kelvin, okay? Now, Q is going to be the amount of heat, okay? A is the surface area. Delta T is the temperature difference in Kelvin. And D is the distance traveled. Okay? You remember we went up, this should be a review from our lectures on heat transfer. Okay. Right. So for the TIMs, the heat spreaders, heat sinks, we want those to be very good thermal conductors. Like the heat sinks usually can be aluminum because we want to make those fins aluminum soft, so it's easier to machine it than say copper. Okay, so we'll use aluminum for those fins, but the copper we typically use for the integrated heat spreader. Okay. Now, why are we so interested in heat management? As we saw previously, if you let the heat run away with you, it will cause the part not to work as efficiently, but it can also cause overheating and you can destroy the part. All right. Now, so when we design, we have to have the correct material selection. So we need high conductive thermal interface for high power parts and for heat dissipation. Okay, if you generate a lot of high power, you got to get that heat out of there quickly. Then if we go to this tin, silver, copper, solder, we do that because it replaces the tin, lead, salt. A lot of, and we talk about green, the lead has to go away. You got to, can't, a lot of municipalities now will not allow any lead manufacturing in their cities, and rightly so. Then, okay, but now we do run into problems with this tin, silver, copper solder, because remember, tin, lead, you have this very low eutectic or melting temperature for the alloy. The melting temperature for this tin, silver, copper is about 43 degrees higher. So if it's 43 degrees higher, that's going to require more energy, more costs. Okay? So we always, as I said earlier, you want to try to keep the manufacturing as low as the manufacturing temperature as low as possible. Okay? Then we will use epoxies to try to absorb some stress, try to cut down on the warpage. Barium titanate for our dielectric capacitors, higher capacitance in a smaller footprint. That's what you want. Okay? Smaller, you can get higher capacitance, smaller footprint. And then we can have our land side capacitors, die side capacitors. Land side, usually the land side is closer to the die, so you can make a direct impact. Okay. Whereas die sides sometimes are further away. But again, it can be based on a design as well. Now, the other thing we got to worry about, like in this particular case where I got my can going on top, profile. Will I have a really thick die? Will I have a thin die? What happens if I have multiple dies of different thickness? Here, in this configuration, I have one die, and hence I only have one die height. That is of concern to me. We want capacitance because we saw earlier when we were talking about our voltage controllers and power supply. We want capacitance high, want a lot of high capacitance so that the impedance, the net impedance will be lower. And remember, we have to also place them in shunt geometry such that, this is true when the capacitance is high. Okay, the impedance is low, but that's putting them in shunt design architecture. Okay, again, we use the barium titanate, high dielectric constant, nickel tin electrodes. Nickel gives you good electrical contact, tin, so you can make good bonding. And then you can, depending on the number of layers, that's how much capacitance you're going to store. Okay, relatively inexpensive, but they have, but they do have size. So you got to think about where you're going to place them on the package. And then we're talking about warpage. Now here, if I have my substrate and I got a lot of differences in coefficient thermal expansion, our die can warp. So what we can do is place a stiffener on, like we see here, which will prevent warpage. Okay. And nice thing about that, by putting the stiffener on, it helps with the adhesive as well. Because, you know, if you're using an adhesive and you get warpage, you know, sometimes the adhesive just can't hold it. But if you put the stiffener on, it can actually help you to secure the package. Okay. All right. I think we got enough time for this. If not, I'll just show you how to do it. For a copper TIMS, where the TIM has coefficient expansion of 8 parts per million per degree C silicon, approximate the maximum thermal stress in megapascals for 82 degrees C change from room temperature. Assume a Poisson's ratio of 0.25 for all materials. So here, when one of these is a film, you got your difference in coefficient of thermal expansion, your temperature variation. Here you have your modulus elasticity of the film, 1 minus Poisson's ratio. So Poisson's ratio is 0.25. Okay. So, now I see people. Okay. Oh. Okay. Okay, so this one says thermomechanical stress can lead to fatigue, crack propagation, warpage, fatigue plus crack propagation plus fatigue. Okay. Fatigue, you need constant loading. Usually thermal stress is 1 stress. So the correct answer would be warpage. So this correct answer would be warpage. Okay. All right. All right. So we'll go back to this problem. So I'm showing you how to do it. So I got copper in contact with tin. The copper is going to be really, really thick. And here you have the tin, which is going to be relatively thin. Okay, so the copper, we're going to say it's going to be 3 millimeters. Tin, 0.5 millimeter. So in this particular case, the tin would be the film. The thinnest one will be the film. If I look over here at this structure, the silicon is about 350 microns thick. And the tin we said was 0.5 micron. So the silicon would be the film, okay? So with the copper, which is really thick, the tin is going to be the film. At this interface, here, the tin is silicon. The tin is, like I said, 0.5 millimeter, silicon 360 microns. So the silicon will be the film. And we will assume Poisson's ratio of 2.5 for all of them. Okay. And I'll just, for the sake of time, just go ahead and show you. Okay. So at the first interface, we'll have the modulus of the TIMS, the difference between the coefficient of thermal expansion for copper and TIM. Poisson's ratio is 0.25. That's 75. Oh, it should be 0.2575. So it should be divided by 0.75. That's okay. And then at the other, it's going to be, don't worry that factor, don't worry about the 7.5. Should be 1.25, but 1.25. So at this interface, 2.6 megapascals. If I look elsewhere at the other interface, I got silicon as the film, difference in coefficient thermal expansion, plug in my numbers. The stress at this interface is much higher, almost 10 times higher than the stress back here. So we have definitely a difference in the difference of coefficient and thermal expansion will manifest itself in thermal mechanical stress. And those stress levels can be high, 1 point or relatively low. On one side, 3 megapascals, 24 megapascals. All right, so you should think about just trying to do some calculations for yourself and look at the thermomechanical properties. So again, we talk about different materials. Those different materials are going to dictate the thermomechanical properties, and they always have to be concerned because you can have, if you don't design it right, or you have bad service condition, you can expand and actually have stress where you're actually touching the can, which is not good. Distortion in sizes, your part's not going to run efficiently, okay? And then if you get runaway, you can destroy it. So bottom line, you want to talk about reliability, manufacturability, cost, performance, you have to select the proper material for your use. Okay. Any questions? All right. Okay. I have to go through here a little quickly. Okay. So part 2. So we talked a little bit about polymers, and we mentioned earlier, we can have polymers that we can use for encapsulation, as well as for a printed circuit board. And we can actually use our polymer TIMs and underfill such that they can help to mitigate some of the stress associated with bonding. Okay. Now, if we talk about polymers, again, poly, meaning mer, unit. We have a lot of little molecules and we tie them together to give us one large molecule. Even amazingly, if we look at a bowling ball, that's one big polymer molecule. Okay. And we talk about the degree of polymerization. Okay, and that's how many of these little units, repeat units here, that we have, the number of those repeat units. And why they're interesting? Because they will influence the higher the degree of polymerization, toxicity. That means when I have these bonds hanging off the side, it'll make it difficult for the polymer chains to slide across each other. So it'll make it stronger. Okay? As opposed to if I do not have these compared to a polymer that does not have any side chains, okay? It'll be more flexible. And the way we have the bond angles and strength will also dictate some of the things like the mechanical properties of modulus elasticity, as well as the chemical stability. And then you ask, why do we use polymers? Well, polymers, in this case, epoxies and silicones, low cost, low weight, okay? And sometimes we will actually use them for dampening. You can tune them to make up fillers, as well as you can, they generally, some of them have good chemical resistance, right? Because like many acids are delivered in polymer containers, okay? So when we talk about polymers, we want to think about the modularized elasticity, the glass transition temperatures, melting point. If it's the thermoplastic, because remember, thermoplastics, they're the egg. I heat them up once, that's it. Concerned about swelling, that's where you will absorb moisture from the air. Some polymers are very effective at it. And so generally you don't want that because they will result in changes in the dimensions. And then we talked about thermoplastics as well as thermosets, right? In one you can recycle, one you cannot. Now, again, the advantages of polymers, good chemical, mechanical properties, easy to mold, process, low weight, low cost. Now, drawbacks, they are low temperature, right? They are sensitive to temperature as well as humidity. And viscoelastic properties, meaning the mechanical properties can change with time. So you have to be mindful of such. And they are much softer and have lower strength than the metals and ceramics. Okay. So in this particular case, again, we didn't talk about toughness. Toughness is how much energy you can absorb at fracture. So aluminum bat, if it'll bend, it'll absorb, difficult to make it break. Whereas the wooden bat is more brittle, so it will crack. So toughness, the amount of energy you absorb at fracture. So these are important things. And don't worry about this one. We already had this poll. We'll just move on. Okay. And oops. We had this one. Okay. So again, polymers are dominant in the semiconductor packaging arena. Okay. They have a lot of unique properties, good properties. We can form them. We can add fillers to change their mechanical strength, thermal conductivity. Just really good material where you can design it or tune it for a specific application. All right. Okay, so any questions? I'm gonna cut through this one. Okay. And
Professor Alfred, I do see one in the chat asking
Okay.
what was the right answer to the last inquiry.
Oh.
And I don't know if it was sent before you said the answer or if it was after we closed it out. Do you want me to reshare that poll result?
let me hold on. Let me
It was thermal mechanical stress can lead to.
Thermomechanical stress can lead to fatigue. So when we heat it up, we stretch, relax, stretch, relax. Stretch, heat it up. You heat up, you spread or extend the length, dimension. Cool it down, you shrink again, heat it up. So that fatigue that's some thermomechanical stress. Crack propagation. Now, so if you have a crack, and now ceramics just inherently have surface flaws. That's just part of ceramics. But when you start cycling and you heat, and then you go too high, you create this thermal stress. And at the tip of the crack, you get a concentrator where the stress is really intensified. You get crack propagation. That leads to catastrophic failure. We've already talked about warpage. Well, you can get, if I can get each one of these three, I can also have them happening at the same time. So I can get fatigue and crack propagation. I can get crack propagation, warpage and fatigue. So I can get all these things happening because all of these properties are sensitive to thermal mechanical stress. Okay.
Professor,
Yes, sir.
why silicon has been selected as a common polymer for semiconductor packaging?
Could you repeat that, please? A little
Why,
louder.
why silicon has been selected as a common polymer in semiconductor packaging?
You said silicone? Wait a minute.
Yes, yes.
Oh, silicone is actually lightweight and has good thermal conductivity for polymer. And one of the things to me, it has good chemical resistance. Silicone is not hygroscopic, so it doesn't absorb the moisture. So, and it can take typical silicone, certain silicones can take the elevated temperature. Because generally, we want to try to keep as much of the processing down below 260 degrees C. Really want to try to keep it below 205. But the nice thing about the silicone, it can take the high temperature, not hygroscopic, inexpensive, good thermal conductivity. And it's been around for a long time. Any other question?
Thank you.
You're welcome. Okay. Okay. Great lead in. Yeah. Now, so when we start talking about epoxies, we'll use them for our substrates, plated through holes. Meaning the holding the printed circuit board and traces together, substrate buildup. again, part of the substrate, printed circuit board, underfill, die attachment, mold compound, everything. Again, excellent chemical and corrosion resistance, good mechanical properties, high modulus, good moduli, high glass transition temperature, good adhesion, low shrinkage. So again, when we start absorbing things, okay. Also, no volatile reaction byproduct. When you cure it, you don't get a lot of solvents escaping. Then good process, you can process it. It's got low viscosity. So we can, before we cure, we can pump it in under the dye into C4 solder balls. And then when we cure, it'll get good flow. Okay. And then we actually can have different ones. We can have resins, again, hardeners, fillers, catalysts to help speed up reactions. We can have coupling agents, help us to make the two polymers stick together. Toughening agents to make them stronger, such that they absorb more energy before they fracture. Okay, we can change their shape. FR4 is flame retardant. So again, a lot of different properties that can be tuned or dialed in. Okay? And why do you want to do it? Let's look at the case of underfill. Well, when we apply underfill, it's gonna heat up during the curing, so it's gonna be hot. It's gonna expand, and then we gotta cool back down. Okay? So when the package cools down, the underfill is gonna help to absorb the strain and deformation. Okay? Now, the solder joints will be compressed, okay, but they will be protected by the underfill, again, to provide mechanical stability. Now, there'll be instances where we'll say, hey, why is it important? Well, we want to, one of the things if we have a crack, and if I get this underfill right, it can actually come in and fill in some of the cracks, okay? So there is like an adhesion layer, but also if it comes in there, it'll help blunt the crack. So it'll reduce the crack probability of crack propagation. Okay? And then we know that it will give us, if we dial it in right, we can actually reduce that solder fatigue because it'll absorb some of that stress. Absorb some of that stress and limit the strain. But again, we have to dial it in. That means we have to know the proper modulize, and we have to understand the coefficient of thermal expansion and what is this effect on toughness. In toughness, you improve toughness by preventing crack propagation. So if we have these cracks and we fill in with our epoxy, it'll help blunt the tip of the crack, reduce crack propagation, improves the reliability. Okay. Now, silicone, as I said, been around for a long time, and sometimes people they can have silicon-based, I should say, grease or phase change material. Nice thing about it is a grease or this phase change, it actually will comply to that surface. Meaning, if the surface is not so smooth, it'll fill in. If I have a crack, it'll fill in. Okay, so that's the great thing about using grease or gels. Sometimes we will use the silicone as an attachment. Okay, if I want a good pneumatic seal, or I don't want moisture going in there, I can utilize that silicone as a sealant. Okay, and then silicone is great because we say it's a toughener. Basically, it's going to get in there. If I do it right, add some mechanical stability and protect this, in this particular case, C4 solder balls, and absorb some of that stress when we go from heating up to cure it, cooling back down to room temperature. So again, cross-link polymers, again, very soft. We can dial in the moduli. Time I hit some kilopascals all the way to 500 megapascals. Very tunable. Very low water solubility, so it's hydrophobic, so it won't absorb the moisture. Okay, so they don't want the water. That means they'll keep their dimension, because if you swell, you lose all control on dimensions. And as we saw earlier, you can use them as an adhesive and a hermetic sealant. Talk about curing. Just when we heat it up, what we're going to do is actually cure or undergo a change in the structure. In this particular case, we're going to increase the temperature. We're going to have platinum as the catalyst to help promote this reaction. Okay. And so with that, we've developed an adhesive that now has a good, strong carbon-carbon bond. Okay. And then a lot of times we will have adhesion promoter. That's just another polymer that will come along to help us make the connection or make a bond to the surface or to another polymer. Okay? And sometimes that adhesion promoter is referred to as a coupling agent. Okay. Then underfill, again, we want low viscosity. We want to be able to once we inject it in the underfill, we want to be able to heat it up, short times, low temperatures. Remember, we always want to operate as low temperature as possible, shortest time, because time is money, and temperature, the higher the temperature, more energy, more costly the process. And then finally, we want to have minimal shrinkage during cure, as well as no volatiles, or very low, because if you have a lot of volatiles coming off as gas, you can end up with a very porous underfill. If you have a very porous underfill, you're going to have low mechanical strength. Okay, so that means we had to understand the different types of adhesives or processing of those adhesives and understand the materials property during the cure. So, there's a lot of innovation that's needed. Materials are everywhere. So with that being said, we won't do, because of time, we won't do this one, but I'll just give it to you. Polyethylene and PVC, they are thermoplastics. Epoxies are thermosets. Thermosets aid. The thermoplastics are water. Heat them up, cool them down, heat them up, cool them down. So epoxies, we have to repurpose. Polyethylene, polyvinyl chloride, we will recycle. So with that being said, we know that the properties of our polymers can be tuned, designed in such a manner by modifying the chemistry, adding additives, whether those fillers to improve mechanical strength, fillers to improve thermal conductivity. And then whenever we are talking about designing parts and trying to accommodate thermomechanical performance, there are going to be trade-offs sometimes between coefficient thermal expansion, viscosity. coefficient thermal expansion, modulus the modulus of elasticity. But again, bottom line, we have to have our material selection such that the material achieves the function that is for which it was designed. We want it to be manufacturable and cost effective. So with that, I'll stop. And do we have any questions? Okay. All right, so we've been going at it. So let's take a, well, people have been coming in and out. Let's take a 5-minute break and come back, and then we will work on our research paper. Okay. So let's say 7 minutes. So be back here at 7:17.
All right, everyone, we'll ask you to start coming back in. We're going to start our next portion of today's activities. So the next part of the agenda today will be to read and discuss trade journals. We will send you into breakout rooms, and every 4 participants will be assigned to one room. You want to make sure that you log into Canvas to access the article link, and then assign those articles to your team members. So there will be 2 different articles and a few guiding questions. You'll have 30 minutes to read the article, followed by 20 minutes of discussion, and then 10 minutes to submit your answers into Canvas. You'll only need to submit the answer for your assigned article. So please note which breakout room you're assigned to. It'll have a number. That way, if anything happens with your internet or you get disconnected, when you rejoin the meeting, I'll know which breakout room to add you back into. I'm going to go ahead and start assigning rooms. Please, if you're not already in your Canvas, please go ahead and log in with the link that I provided in the chat. And then give me 1 moment and we'll get you into those breakout rooms. If you have any questions, you're welcome to send me a chat or pop back into the main room and we'll get you we'll get your answers. Let's see. All right, you'll start receiving those requests now and go ahead and just click to join those breakout rooms. You should see a pop-up asking you to join a room. Please go ahead and click that so you're able to join in. Seeing quite a few people still in this main room. So as you're returning from your short break, you should see a breakout room invitation. Please go ahead and click that and join your breakout rooms. We're going to be doing 30 minutes of reading the articles and then go into some group discussion for 20 minutes. I'm seeing quite a few people still in this main room. Please let me know if you're having any trouble or if you don't see the invitation for the breakout room. Welcome back. If you're just joining us, we're going into our breakout room sessions now. We're going to be reading articles and then coming back for discussion in about 30 minutes. So please go ahead and click that button to join your breakout room. and you'll select which article you're going to read. Anybody having any issues with the breakout room? Please unmute and let me know, see how we can help you. Marco, welcome. I see you just joined us. We're actually heading into breakout rooms to discuss the trade articles. I can go ahead and get you assigned into a room. And welcome if you've just joined us. We are going into our breakout rooms. We have, let's see, we've got some trade journal articles. I've posted the links into the chat. You'll want to log into your Canvas account. Reach out to me if you have any challenges with that, but I'm going to go ahead and assign you into a breakout room. And you'll want to take 30 minutes to read those trade articles, probably about 20 minutes at this point. And then you'll have some group discussion and then submit your responses into Canvas. So all in all, from here, you'll be in there about 50 minutes, and then I'll close out those breakout rooms. 1 minute, and I'll get you all transitioned into a room. Edward, I see you just had joined into the main room. Were you in a breakout room before I can return you to, or are you just joining us? Okay, I'm gonna go ahead and try to move you into one of these breakout rooms if you just accept the invitation. And hello, Mauricio. I see you're just joining us. Or if you're just joining or just coming back, let me know if you were already in a breakout room and I could send you back to that same room. Otherwise, we are getting into articles from the trade journals and going into some small group discussions. We've got about 20 minutes left to read those articles and come back into the group and then submit responses into Canvas. So feel free to unmute if you were already in a room. Otherwise, I'll get you assigned into one. welcome if you're just now joining us. We are in our breakout rooms and reading some trade articles. Got one more joining us right now.
Yeah, please get me in one break room. Thank
Oh,
you.
sorry, could you repeat that?
Yeah, can you give me a break room so that I can join in one of the break room?
Yes, absolutely. I'll get you transferred into a break room. Let me just see which one has less people than others. And then in Canvas, you'll be able to see the article that we're reading. There's about 15 minutes left to read the articles.
Yeah, Brittany, can you hear me now?
Yes.
Thank you. You wasn't able to hear me from my computer, so I switched to my phone. I was looking on the canvas, but unfortunately, I don't see the task. I see the last 3 courses, but not this one. So I have
Okay.
only 3.
Got it. I'm going to repost in the chat just the links to these trade articles so you can get started. And then let me resend the link also for the,
Yeah, but my question is, where do I submit it? Because I don't have I mean,
Yeah.
I have access to Canvas, but I don't have
so I
like
will resend you the link to the course so that it'll show up in your Canvas account.
Okay, perfect.
Yeah, or if you go, so are you able to log into Canvas and you just can't see the course? Is that right?
Yeah, I can see the courses, but only the first 3, not the one for today.
Okay. Yeah, some other folks are having issues with it as well. Let me resend the link over, and then the other option, let me try to resend the link and see if that'll work.
Sure.
I'm trying to get to my chat, but it's not working with the all the things I have shared. Here we go. Okay, I'm gonna post this article into the chat so you can at least see what the assignment is and the questions. And maybe copy and paste those real quick, because I don't know if you'll be able to see the chat once you go into your breakout room.
Sure, but my question is, where do I submit it? Because
Yeah, I'll do that. I'll send you to the breakout room, and then while you're in there, I'll resend the Canvas.
okay, just give me just a sec, just to copy this.
Yes. Yeah, don't worry. I just didn't want to make you sit here while I went into Canvas to do that.
Okay, let me just check the links because the links didn't copy.
Oh no.
Copy this.
Okay,
I'm just copying this into WhatsApp, so it will be easier.
sure. Let's see. Can you tell me the let me search it real quick. Mauricio, it shows that you have a pending pending for the course. So let me do this.
But I have a question also because I have like 2 emails registered. I have the ones that says armas.mauricio823@gmail.com, and I have the one from the university that is mauricio.armas@uhispano.ac.cr.
Okay, let me check really quick which one.
But the one I'm using right now is the first one, the armas.mauricio823 one. That's the one I have the assignments on.
Okay, just a second. Let me just see what's on here. Would you mind just putting into the chat just a direct message to me?
Sure.
The email address that this is supposed to go to, and then I'll make sure that I resend one to that email.
Absolutely. Just give me a sec. At gmail.com to Brittany Holmes. Okay.
Perfect.
There you go.
Okay, let me do this. And there should be a way we could sort of merge those accounts, I think. But for now, let me just go ahead and get you added here. Student. Okay, That should be sending it right now to that Gmail account.
And let me just double check I received it. Just give me a sec. Just to make sure.
Perfect.
Nicole, I have one for Nicole.
And then I see someone else is adding to the chat another email address. Sounds like you're also having problems with Canvas, so I will also do a addition there. Let's see.
I have one link from Nikki, like
Itzy?
10 minutes ago. Yeah, but from Nikki, just the link for today, but not anything from you.
It probably wouldn't show up from me. I'm logged into our executive email account. So
Okay.
it might actually show up from Nikki. So maybe see if it has the right link in it or not. Because Nikki, I think, is listed as the contact for the course.
Okay, perfect. But I have the link for the call, but not for Canvas.
Okay, let me try this. I'm going to post the Canvas link that goes directly to the course in the chat.
Perfect.
And let's see if you click on this, if you can get to the course now.
Yes. Structures. Okay, let me just copy it. Just get to it. Okay. Okay, now I have the invite here.
Did it work? Sorry, I didn't.
Yep, seems like. Let me just double check
Okay.
here and the inbox as well. Assignments. Production thermals and conductor packing and design. Packing materials, manufacturing, test and availability. And let me just check. Yep, now I have the fourth course. Perfect.
Okay, yeah, it's probably just depends on which email address you're logged into, for which ones you can see. So I don't know if it's possible to merge those accounts, like to have two email addresses that both work, but it might be worth asking.
Yeah.
So
Actually, I don't know why, because the first three I just received it like, well, it's just this fourth one that had the issue that I didn't have it on my on my inbox. So I have like the three tasks. I mean, from the task on the test for the three main courses, but not for this one. But now I have it.
strange. Okay. Okay, perfect. So is this Gmail the one that you prefer to have stuff sent to in the future?
Yes, please.
Okay, that's really helpful. Let me update that in my list. Otherwise, I think they'll keep going to your other email account. Okay, perfect. Are you good for me to send you into a breakout room? There's only a few minutes left before they go into discussion.
Yep.
But there's about 5 more minutes left until I'll send a broadcast out to return to discussion.
Okay, absolutely.
Let's see, I'm
Sounds
gonna
good
add
for me.
you into, I think room 13 only has 3 people, so
Okay, perfect. Thank you, Brittany.
thank you.
Bye. Bye for now.
Bye.
Yeah, dear professor, could you please extend the final exam for course one and course two? I have some hospital problem in 2 weeks, so I forgot to do the final exam for course one and course two.
I understand. Yes, we can open that back up for you to take the final exam. Would you please put your email address you're using for this into the chat? Just
Yeah,
a direct message over to me.
yeah, I will write my email into the chat for you. Right. Could you please check the direct message?
Oh, yep. Okay, I see you. Final exam for course 1 and 2. Okay. Let me see. Let me have them do this for you in our morning time. I did it with one other course and I'm not confident that I did it correctly. So let me put you on our list to get to in the morning if that's okay. And
Yeah.
then you'll be able to have access to take those final exams. We could give you access for a few days.
Yeah, so thank you. Please extend the final exam for course one, course two for me.
Yep, the first and second one for this badge, and I've got your email address here. Okay. And can I return you into a breakout room?
Yeah, I will come to my breakout room again.
Were you in one before that you want me to resend you to?
Yeah, I joined the room 18 already.
Room 18? Okay. Okay, I'll send you there now. Hi, Joey. I see you just joined us. Were you in the session earlier? Can I return you to a breakout room, or do you want an overview of what we're working on right now?
Hi, I'm actually still connected on another device. It just didn't switch. So I'll just wait for the sessions to finish before I switch to my computer.
Oh, okay. Sounds good.
Thanks. Yeah, just double checked. I'm still in room 22. Thank you.
Okay, perfect. But you want to stay in this one, or you want me to sign you back into 22?
That would be great if you could do that. Thanks.
Okay, Hello, Jose and Het. Nice to have you join us. If you were already in a breakout room, please let me know and I can return you to it. Otherwise, we are just finishing up our reading and discussion time, and we're gonna, in about 3 minutes, we'll start putting our feedback on articles into Canvas. So unmute and let me know if I can return you to a room. Otherwise, I would just hang tight. And if you haven't already read the articles, I will repost those into the chat.
Wow. Thank you, Brittany. Yeah, I was teaching also on another class, but I don't want to miss the discussion right here. But you want to put me on a room, or I can also start reading. You know, I'm running a little late on the homework, but I will.
No problem. Yeah, so there's only 2 minutes left of discussion. So have you tried logging into your Canvas account yet to reach
Oh
this?
yeah, I can log in
Okay.
without any trouble. So I'll start reading right away. Thank you very
Okay,
much.
perfect. Yep, I would just get started with that and then you just need to submit those
Sure.
question answers in a few minutes, or you'll have beyond today, but
Great.
go ahead and
Thank
submit
you.
those when you're done.
Thank you very much. Oh, really? You have the names of the two articles?
Yes. Let me post these into the chat that has
Sure.
the article links and the questions. They're also should be in Canvas.
Yeah. I just
Okay.
asked to be sure that they are the ones I'm reading.
Yes. Okay, here we go.
Thank you.
Yes. Thank you, everyone. I see you slowly trickling back into the main room. We're just gonna wait for everyone to return back in here. Give it another minute. Okay, Professor Alfred, it looks like we've got everybody back into the main room. Were there any closing thoughts or remarks that you wanted to touch on before we let folks go today?
Okay. All right. And I have one, I found my little review. I would like to do that one as well. Won't take only a few minutes. Today, new interconnect metals need new dielectrics. Well, yes, if you go back to 1998 through 2006, a Motorola, Apple, and Intel were pursuing this new metal called copper. And whereas Texas Instruments and a few other companies, they wanted to ride aluminum all the way out and look at low-K dielectric materials. So they did a lot of work in looking at low-K dielectric materials. And one of the challenges about these low-K that they were doing, they were looking at these organic silanes, but when they did it, it would actually introduce porosity. Now, if you had this complete 100% porosity, that's definitely low-K dielectric. But one of the problems with this porosity, you lost mechanical stability. And so it just didn't work out, just couldn't get it to work. And eventually they had to move on to copper metallization like the rest of the industry. But this new paper has identified the fact that you can introduce some polar molecules to this organic silane, and you can actually introduce some porosity, maintain mechanical stability, as well as reduce the dielectric constant. Because one of the things also about introducing porosity, it will affect your etching. It will make your etch rates non-uniform. So with this one, yeah, that mechanical stability, integrity of the material is going to be the true challenge. And then can you balance this amount of porosity in there such that it's uniform, and so that you get a good, nice, uniform etch, as well as a nice, uniform chemical mechanical polishing when you do your planarization. And moving forward, yes, we will have to go to these metal organic frameworks if we want to go at low-K dielectrics. Because we talked earlier, we were looking at our voltage controllers, and we saw, well, I do create these parasitic capacitors. Well, if we want to reduce the overall dynamic capacitance, we need to lower any of the leakage as well as the dielectric constants with dielectric constant associated with metallization. So yes, we will have to move forward with these metal organic frames and try to get as close to an air gap as possible. Okay. Get to an air gap, that's the best. Okay, and then copper for redistribution. Well, now these individuals talking about looking at redistribution lines that were 5 to 20, 5 to 20 nanometers. Microns, excuse me, microns. Now, they were prone to what we call joule heating due to electromigration. Electromigration, I think we talked about it last week, where you have such a large flux of these teeny tiny electrons, they can transfer momentum. And in doing so, they can actually initiate a void. Then once they initiate the void, the cross-sectional area is reduced. So that means the current density increases. Then you keep doing it to a point where you actually cause an open. That's referred to as the fusing current. Now, that's the current you drive till you actually create an open. Well, I disagree with their saying about fusing currents. Go back to 1944 and 48. I've written at least 2 papers, or my students, let me get it correct. My students and I have written 2 papers, at least 3 papers, talking about fusing currents in silver metallization, and aluminum metallization. Because at the time we were working with Phillips Design Center, and we were trying to build these inexpensive voltage controllers on one mass set, so that we would just build one mass set, and then we would blow a fuse if we want to program it for 0.8, blow a fuse if we want it for 1.2, blow a fuse for 2.5 volts. And so we did studies looking at fusing currents. Now, what you don't want is have a fusing current, because what it will do is actually create opens. Now, in that case, we were trying to build fuses that we could program. Where here, what they've seen now is that as we go to smaller and smaller feature sizes and more levels of metallization, that if we overcurrent, you can lead to joule heating. Now, there have been, anytime you get above the melting temperature, and think about it, you're heating this thing up, but you force so much current through it that when you drive that current, it just vaporize. So now you're left with an open. And if you keep reducing the cross-sectional area, that current density, the joule heating goes up as J squared. So now the more current you drive, the quicker you're going to get to that melting temperature. So they're going to, in this article, they talk about trying to predict when would you have fusing. Okay. And I think the experimental approach is actually to run electromigration studies on structures that are similar to your redistribution layout or your wafer level layout. Do those benchtop studies and then move to test vehicles that are common to the packaging industry, ball grid arrays, or under bump metallization, to do the tests to see how those parts will also be effective when you get to the high joule heating. Okay. And by doing it, hopefully you'll be able to ensure that you're getting some reasonable experimental data, such that now you can take that and help you try to do some modeling and prediction of failures. Does anyone have any questions? All right. And then lastly, okay, we're gonna do, I found my thing. So tonight, oh, no, excuse me. We're gonna do this little exercise and you're gonna post it. I forgot, Brittany, have they already posted their reviews or they're gonna do that later on?
Yeah, so we included time in that hour to post the reviews, but if you need more time, you can post them after class today as well.
Okay. All right. All right. So let me do this. Well, I'll leave this for you. Well, these are, oops. Now I gotta find my Zoom. Zoom. Okay, so here, we're gonna just go through these. These few questions are just true, false. And, oops. Okay. And then you could just, someone can just raise their hand or, let me see, where to my Zoom again. Oh, there. Okay, or you could just unmute yourself and give the answer. So it's true, false question. Fracture is a prone failure mode seen in electronic packaging. True or false? Just go ahead and unmute yourself if you have 101 people. So 99. Hello? Okay. Fracture is it is.
Do you want me to send this out as a poll, Dr. Alfred? I can.
Yeah, I
You
was
can put
waiting
this
for
in
the
poll
poll,
mode.
yeah.
Oh, okay. So yeah, I guess you want to do, how difficult would that be to do?
I'm just gonna do it right now. Just give me 1 second.
Because then we could just do true, false on each one of these and because it'll be the same, we just reuse the poll.
Okay.
My error. Yeah, we could just do true, false.
Ah,
It would take 10 more seconds. Oops. We're still chiming in. Okay. fracture, okay. Yes, it is true. And Brittany, can we just reuse this poll, but just take the question away? And just have no
Yeah,
question?
let me just do one, and I won't put a question in, and I'll just write true, false. Otherwise, I don't want it to add to the other answers
Okay,
that were already input, but here we go. I can do that really quickly. There you go. So this one's ready when you move to the next question.
okay. Strain gauge testing is used for semiconductor packaging characterization. True or false? Okay, we got 10 more seconds. And that is true. Last night, Dr. Theodore talked about strain gauge testing and various testing techniques. So that is correct. Okay. So true. Okay. Typical fatigue and electronic packaging is high cycle fatigue. It should be typical fatigue in electronic packaging. It will take 10 more seconds. In the poll. This is false. The typical fatigue in electronic packaging is low cycle fatigue. High cycle fatigue is where something is going very fast. That'd be like a turbine blade. Here, typically the heat cycles are heat up, cool down, heat up, cool down very slowly. So this was actually false. It's low cycle fatigue. Okay. Fatigue is common phenomenon of solid joint failure due to materials mismatch in the coefficient of thermal expansion, resulting in thermomechanical stresses during temperature cycling. True or false? Well, can we have our poll?
Yeah, sorry about that.
No
There we
problem.
go.
There we go. Hey. Take 10 more seconds. yes, it's true. That is the fatigue is a common phenomena, and it is due to cyclic tests, thermal cycling, heating up, cool down, and differences in coefficient thermal expansion. Okay. Okay, solder joints are subject to fatigue loading during thermal cycling. So that was essentially the same question. Let's skip that one and go. Oh, here's a good question. Creep is a time-independent elastic strain phenomenon in materials under sustained load at elevated temperatures. True or false? And can we have our poll, please?
Oh, sorry, it says on my end that it was launched. Let me
Oh, maybe I don't see it.
go back. And try that again.
Do you see it?
No.
Sorry, everyone. I'm working on getting a new one up. Just keeps saying it's been launched, so I think it wants me to make a new one.
I'm sorry about that.
1 second. Oops.
We take 10 more seconds. This statement is false. Creep is a time-dependent elastic strain phenomena in materials under sustained load at elevated temperatures. Yes, it is time-dependent. It's a function of time. Okay. And then it's our last one for the evening. Oops. And creep occurs at temperatures less than 1/2 times the melting temperature of the material. In this particular case, we're talking about in metals. True or false?
Sorry, everyone. I keep getting the same issue where I create it and then it doesn't let me launch it. So let me try one more time.
Okay, we'll try one more time. If not, we won't bother you anymore this evening. Okay. Well,
Yeah, Sorry, it's just not, I'm getting no button to launch.
Okay, no problem. But I'm looking at the chat. We're 100% with false, and that is correct. Creep occurs at temperatures greater than 0.5 times the melting temperature, or it says it's most active because it's a thermally activated process, so it's got to be at elevated temperatures. Okay, so that is it. Now, do we have any questions from tonight? Any questions for me? Let me open up. I don't see.
I got a private question in the chat asking about some assignments that folks could see that were not supposed to be published in there. So the only assignments relating to your grade, and I think we fixed the issue, but in case you saw anything in the Canvas shell, we should have fixed it now. And so this is the grades for this will really just pass, fail from the trade journals and the exam at the end. So if you saw other assignments in there, disregard them. They should be removed now, and sorry about that.
Okay, well,
Thank you, Professor. It was a great session.
oh, thank you. Yeah. But I'm glad you all were able to participate, and I hope you were able to glean something that was of interest to you, and something that would advance your understanding and your interest in semiconductor packaging. All right, with that, I will just have to say good night or good morning. I mean, I should say good day or good night. All right. Take
Thank you,
care.
Professor.
You're welcome.
Thank you. Good night,
Professor.
Professor.
Good night.
Thank you so much. Yeah.
Bye, everybody. Good night.
Thank you.
Thank you.
Thank you.
Thank you,
Thank you so
Professor.
much.
Welcome.